Hello and welcome to today's lesson on how gears work, which is part of the forces topic in GCSE separate science physics. So we're going to really focus in today's lesson on how gears work. So if we are successful and learn in this lesson, we should be able to define what a moment is and link this to gears, understand how a simple gear system can be used to transmit the rotational effects of forces, and then finally explain how gears transmit the rotational effect of forces, which is part of the following part of the GCSE separate science physics specification 4.5.4 moments, levers and gears, which is a separate science only content of the course. So gears can be used to increase or decrease the moment of a force in a system. Now gears are simply wheels with teeth around their rims. So the circular discs have teeth around their edges, and these teeth interlock and cause one disc to turn another disc. Now it's important to note that in all gear systems the wheels rotate in opposite directions. This means the first disc transmits the rotational effect of the force to the second disc in the system. So for the two gear cogs, it's important to note that the power, the energy and the force between the two is constant, but for these two circular discs, the moment of each disc can change. Now it's very important to note that different sized discs can be used to change the moment of the force. So a force is transmitted to a larger gear, which will cause a larger moment as the distance from the interlocking teeth, which is where the force is, to the pivot is going to be greater. So we can see here the larger the gear wheel, the larger the distance between the pivot and where the force is exerted, so you get a larger moment. And obviously for a smaller wheel, there's a smaller distance between the pivot and where the teeth interlock, so therefore there's a smaller moment for this particular wheel because there's the same force being exerted on each wheel in the gear system. So let's just clarify this. A gear is a mechanical system where at least two wheels interlock. So this interlocking allows for the forces to be transmitted between the two wheels. Now in a gear system, the power remains constant across both wheels, so therefore the energy across both wheels remains the constant. Now the force acting on both wheels is the same due to Newton's third law. If you have two objects exerting a force on each other, they will be equal yet opposite. So what this therefore means is that if you have two wheels which are interlocked and are the same size, the moment of each wheel and the speed of each wheel will be the same. The only difference will be is the two wheels would rotate in opposite directions, because remember, in all gear systems the wheels rotate in opposite directions. But there are gear systems where the input wheel, the driving wheel, is larger than the output wheel. This will be a high gear. Now a high gear is where a larger wheel is interlocking and causing a smaller wheel to rotate. Now this allows the output wheel to have a higher speed yet a lower moment or turning effect. So this is important. It has a lower moment or turning effect as the distance between its pivot and where the two wheels interlock is smaller than for the input wheel, so therefore it will produce a lower moment because the force is the same but the distance is smaller. But because the wheel is smaller, it will rotate faster, so it allows an object to stay at a similar or faster speed. So this is where we would use a higher gear on a bike or a car. Now there are some gear systems where the input wheel is smaller than the output wheel. This is a low gear. So you'll notice that in a low gear is when a smaller wheel is interlocking and driving a larger output wheel to rotate. Now you'll notice the output wheel is larger, so therefore it will have a greater moment as the distance between the pivot and where the two wheels interlock is larger. So for the same force, a larger moment is produced. However, because it is a larger output wheel, it will rotate slower. So this allows a larger turning effect or moment, yet a lower speed. So we would use a low gear to allow an object to start to overcome inertia. So a lower gear means you don't need a big effort to move because this larger turning effect is provided by the gears. So let's look at an example question. A gear with a radius of 0.1 meters is turned by a gear with a radius of 0.05 meters. The moment of the smaller gear is 20 Newton meters. Calculate the moment of the larger gear. Now, firstly, our instinct is that because we have a larger wheel or gear, it is going to have a larger moment. So let's see if that's the case. So the first step is to calculate the force on the teeth of the smaller gear, because we know the moment is 20 Newton meters and we know the distance is 0.05 meters. So force is moment over distance, so it's 20 over 0.05, which is 400 Newton meters. Now, if there's a force of 400 Newton meters on the smaller gear, there must be a force of 400 Newton meters on the larger gear, because the force is the same for both the wheels. So therefore we know moment for the larger gear is force times by distance, which is 400 times by the distance between the pivot and where the wheels interlock, which is 0.1 meters. So our moment is 40 Newton meters. So turning a gear that has double the radius doubles the turning effect, so it's a double of a turning effect multiplier. So like our instinct told us, the larger gear has a larger moment. So gears are used to change the moment of a turning effect. So to increase the moment of a turning effect, a smaller wheel needs to drive a larger wheel. This is a low gear. So this means there's a greater turning effect which can overcome inertia or resistive forces more easily. To decrease the moment of a turning effect, a larger wheel needs to drive a smaller wheel. This is a high gear. This means there's a greater velocity, so it accelerates easier. However, it's more susceptible to resistive forces because our moment is smaller. Now we can calculate the moment found on different gear wheels, and this allows engineers and physicists to measure the change in the moments in the different wheels of the gear system. So we can calculate a moment with the following equation. The moment of the wheel in Newton meters is equal to the force applied in newtons times by the distance from the pivot in meters. Now when considering the gear wheel, the pivot is the center of the wheel. So this means the distance from the pivot is going to be the radius of the wheel. So the moment of the wheel in Newton meters is equal to the force applied in newtons times by the radius of the wheel in meters. Now remember, in a gear system, the force is kept constant across all of the wheels. It's the speed and the moment that can change from wheel to wheel. The larger the wheel, the greater the moment it produces, because the force is the same but the radius of the wheel is larger. But because the wheel is larger, the wheel will spin slower. And remember that if the two wheels are the same size, the moments, the speed and the forces are all equal, but they will act in opposite directions, so will rotate in opposite directions. So let's look at an example of this. A gear wheel of radius 40 millimeters is used to turn another gear wheel of radius 20 millimeters with a force of 60 newtons. So what's the moment of force on the 20 millimeter wheel? So moment is force times by radius, so you would work it out to be 1.2 Newton meters. But it's important to note is how can we work out the force, the moment of the force on the 40 millimeter wheel. Well, if there's a 60 Newton force on the smaller wheel, there'll be a 60 Newton force on the larger wheel because force is constant. So you now multiply that force by the radius of the wheel, and it's now 2.4 Newton meters. So once again, it tells us that the larger the wheel, the greater the moment or turning effect produced, but the slower the wheel spins. Yet the smaller the wheel, the lower the moment or turning effect produced, and the faster the wheel spins. So you should be able to understand how a simple gear system can be used to transmit the rotational effect of forces, and then explain how gears transmit these forces. So if we've been successful and learnt in this lesson, we shall to define what a moment is and link it into gears. We should understand how a simple gear system can be used to transmit the rotational effect of forces, and explain how gears can transmit the rotational effect of forces. So I hope you've enjoyed today's lesson on how gears work, which is part of the forces topic in GCSE separate science physics. Thank you very much for watching and have a lovely day.